Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're joining us today because we're going to tackle a truly foundational algorithm in data science. Our goal? Demystifying k-means clustering. Now, if you've spent any time at all looking into machine learning, you know k-means carries this heavy reputation for dense, intimidating mathematical formulas. But you know what? The underlying visual intuition is actually beautifully logical once you break it down. So today, we're going to look at that visual intuition, the core mechanics, and the practical reality of this algorithm, so you know exactly what k-means is doing behind the scenes.
Here is our game plan for today. First, supervised versus unsupervised learning. Second, the art of clustering. Third, how k-means works. Fourth, the math and convergence. And finally, real-world limitations. Okay, let's dive right into this. Section 1, supervised versus unsupervised learning. To really understand k-means, we first have to understand the environment it operates in. Take a look at these two scenarios with our little robot friend here. On the left, we've got supervised learning. The human literally holds up a picture of an apple, and the robot learns to identify it because it's been handed the answer key. It asks banana, the human says no. It asks apple, yes. It has perfectly labeled data to guide it. But look over on the right. That is unsupervised learning. The poor robot is just left staring at a completely unlabeled bunch of fruit on the table. Now, it manages to group the apples and the bananas together based on their physical features, but it looks back at the human kind of like, hey, is this right? There's absolutely no answer key. The robot just has to find the inherent structures and patterns hidden within that unlabeled data entirely on its own.
So moving right along to Section 2, the art of clustering.
To help an unguided, completely in-the-dark robot like the one we just saw, we use clustering. To put it crisply, clustering is the process of grouping discrete, unlabeled data points into distinct categories based purely on their similarities. It is literally the ultimate solution for our unsupervised learning scenario. We just hand the computer a massive, messy pile of unorganized information, and we ask it to find the natural boundaries. But before we look at how a machine actually pulls this off, let's look at how human intuition handles it.
Let's try a relatable human task. Actually, I want you to actively play along with me for a second here. We've got 5 documents, right? Each one has a few keywords. Doc 1 says health, medicine, doctor. Doc 2 is machine learning, computer. Doc 3 is environment, planet. Doc 4 is pollution, climate crisis. And Doc 5 is COVID, health, doctor. Now, if I asked you to sort these 5 mixed-up documents into exactly 3 logical groups based on their meaning, how would you do it? Just take a mental second right now to sort them.
Okay, so if you're like most people, your brain instantly kicked into gear looking for patterns and highlighting themes. You probably noticed right off the bat that Document 1 and Document 5 both share heavy medical themes. You know, words like doctor and health. Document 3 and Document 4 share very clear environmental themes, talking about the planet, pollution, and the climate crisis. And Document 2? Well, that one seems to be sitting in a technological lane entirely of its own with machine learning and computer. Notice something? You didn't need a math equation to do this. Your brain just naturally calculated the similarities on the fly.
And boom, here is that final clustered result, beautifully color-coded. We've got the blue medical group, the green environmental group, and the orange tech group. This totally intuitive human clustering maps perfectly to the ultimate goal of unlabeled data categorization in machine learning. We essentially want the algorithm to do exactly what your brain just did, but we wanted to do it on a scale of millions of data points instead of just 5 documents.
Which brings us to Section 3, how k-means actually works.
So now that we understand the goal, let's enthusiastically break down the mechanics. K-means operates through a very procedural, almost rhythmic repetition of basic steps. I actually really like to think of it as a mathematical dance. Step 1, it randomly assigns cluster centroids. Just think of these as the initial anchors or starting points dropped onto a graph. Then, it enters a loop that just repeats until the dance is totally over, or, in technical terms, until convergence. Inside this loop, it performs Step 2, the cluster assignment step, where every single data point looks for the closest centroid and joins its team. Then comes Step 3, the reassigning centroid step. This is where the centroid physically moves itself to the literal center of its new team. And then, it just repeats those last 2 steps over and over again. And I love this because it brilliantly illustrates that exact dance. Guide your eyes carefully through these 9 panels with me. Starting right up at the top left at Panel A, see those uncolored green dots? That is our unlabeled data. The blue and red X's are our randomly assigned centroids. Now look at Panel B. The algorithm draws a boundary, assigning every dot to whichever X is closest. But notice what happens in Panel C. The X's have moved.
they reposition themselves to be dead center within their newly claimed points. Because they moved, the boundaries have to shift all over again in panel D, which actually causes some points to switch teams. As you follow the panels down to G, H, and finally I, you can see the blue and red centroids acting like magnetic anchors. They keep adjusting, gathering their closest points, shifting slightly, gathering again until finally, they just settle. The boundaries stop moving. The algorithm has officially converged.
Now, what's really interesting about this next part is how we actually score that dance. Section 4, the math and convergence.
Okay, don't let the text scare you, because the core logic here is surprisingly simple once you translate the dense math. The official literature says the goal is to organize the data such that the sum of the squares of the distances of each data point to its closest vector is a minimum. Right, so let's put that in plain language. Imagine the centroid's a team captain standing out on a field, and the data points are all the players. The algorithm simply wants to minimize the physical running distance between every player and their respective captain. That's it. If moving the captain to a totally new spot reduces the total distance everyone has to run to gather around, the algorithm absolutely makes that move. It just wants the tightest, closest knit groups physically possible.
And to keep this organization perfectly clean, K-means uses what's called a 1 of K coding scheme. Basically, this is a strict binary system. We're talking zeros and ones only. A data point gets a 1 for the cluster it belongs to and a 0 for literally all the others. There is no sharing here. A data point cannot be 60% in the red cluster and 40% in the blue cluster. It's a strict, absolute yes or no rule that prevents a single data point from ever belonging to two clusters at once. You are either entirely on the red team or entirely on the blue team.
But, as we know, Section 5, Real-World Limitations.
Theoretical perfection rarely survives contact with reality, right? Let's rapid fire through some of the major practical issues you're going to encounter when you deploy this on actual datasets. First up, the algorithm doesn't magically know how many clusters exist. You have to tell it the optimum K, the number of groups. And often, humans still have to visually look at the data to pick the right number, leaning right back on our own intuition. Second, it can converge to a local rather than a global minimum, meaning depending on where those X centroids randomly drop at the very beginning, the algorithm might get stuck in a good enough arrangement, completely missing the absolute best mathematical grouping. Third, it is highly sensitive to outliers. Because it's obsessively measuring distance, one crazy data point way out in the middle of nowhere can drag a centroid entirely off target. And finally, because of these strict mathematical assumptions, it often really struggles generalizing to highly complex, irregular data shapes.
Which brings us to the ultimate drop-the-mic question. We've seen how beautifully simple and intuitive K-means can be, but we've also seen its glaring flaws when faced with the absolute chaos of real-world data. So I leave you with this. Is this strict, rigid, distance-based algorithm really the most optimum way to look at the problem of categorization? Or is there a completely different way for artificial intelligence to actually understand the subtle, messy nuances of the world around us? Just something to think about. Thanks so much for joining me on this explainer, and keep questioning the data.